And this activity is going to review some of the fundamental theorem of calculus part 1, which is something we always need to review because we hardly use it until it comes up on the exam, and then you're like, oh, I wish I would have reviewed that. And the fundamental theorem of calculus part 2. It also has on the second and the third pages actual FRQs. And those are the long answer questions on your exam. Your exam always has 6 of them. They're worth 9 marks each. And they usually encompass the whole course in each kind of question. So, or sort of take one of the last concepts you learned and connect it to all concepts that would have been before. And now that we're into integration, we're able to start doing some of these because integration is considered the last concepts. Okay, so we'll get an idea of that. Now, what I'm going to do with fundamental theorem of calculus part 1 is we're going to do a couple of these together because you haven't done them for a while and they make you think. So first of all, how do we recognize the fundamental theorem of calculus part 1? Is you have a variable in one of your bounds. This is going from 1 to x. In the fundamental theorem of calculus part 1, the number at the bottom doesn't matter what it is. If you're going up to x and you want to find the derivative, so fundamental theorem of calculus part 1 is finding the derivative of an integral. And if you're going up to x, the derivative is just to replace the function with x, it's x cubed. And if only they would just stay at this easy level, you could do 1,000,000 of these in your sleep. Okay? The second one I'm going to leave for you to do because it uses a property. It has the x, but the x isn't at the top. So you're going to have to use a property. But then we had the questions where there wasn't an x, there was some other function that included an x, so we'll do c together. You're going from 2 to 3x squared of 2t cubed. Okay? If you're going up to another function, some people go straight to the answer. Just like you replace the equation with an x, now you replace the equation with a 3x cubed. But you always have to do a chain rule and add it in. When we were understanding it, when we were first learning it, we did a substitution. And that substitution allowed us to rewrite y equals, and then go from 2 to u, and have and then instead of finding dy dx, you were finding d du, but that meant that you had to have add a du dx at the end. That was the substitution that we did. Okay? Most of you will probably eventually just go straight to the shortcut. The shortcut says, do it exactly the same as we did the first one, which means we replace the t with the number at the top, but then you have to multiply by the chain rule at the end. Okay? Problem with the shortcut is you're using just a memorization technique. You're not really understanding what's going, you're just knowing how to get the answer quickly, which is not bad. But it's good to remember that the substitution allowed us to do that. So if you remember that the substitution allowed you to do that, feel free to use the shortcut and say, well, I do know what's going on, but the shortcut gets me my answer very quickly. And then if you wanted to, you could simplify this. And then I'm going to do one more together with you. We're going to do D together because it is completely different. We have not seen one like this before. We can use the fundamental theorem of calculus part 1 when you have an x or any function in one of your bounds. But now we have an x in both of our bounds. And the fundamental theorem of calculus doesn't do that with both of our bounds. So what can we do? We can cheat. We can use one of our properties and say, well, let's just put a value in between those bounds. Doesn't even have to be in between them. Pick any number. Pick 0. Or if you want this question to be longer, pick 2,357,815. Just have to write more. And so the property says if you pick a value going up to that value, a one integral plus the other one would be the same thing. This one has our x on the top with a function, so we're going to have to use the chain rule. This one has the x on the bottom, so we're going to have to use our properties, say, I can put it negative and switch those from bottom to top. My derivative then will be the derivative of the first one, which is just x and then a negative in front. Derivative of the second one will just be cos x, but then you have to do the chain rule and multiply by a negative sin x. So that's part 1, and I'm going to get you to start working on those. I'll do one question on part 2 together. Use the fundamental theorem of calculus. This is technically fundamental theorem of calculus part 2, but it is often referred to as the fundamental calculus theorem of calculus because part 1 is ignored a lot. It's feeling that's like the bad child that nobody talks about. This is what's used the most. So what do? We integrate with square brackets. We write our bounds. And this is what we've been doing lately. I probably don't even need to show you one example of this. But then you plug in the top number, subtract, plug in the bottom number, and get a nice answer. So we've got a function here, f. We're told that g of x is the accumulation of change from 6 up to x. So starting at 6, accumulation of change after that. Find g prime of 8. Okay? G prime of x is equal to f of x. Give a reason for your answer. This is really important that we start, like, you are allowed to use FTC. EVT, MVT, IVT, you're allowed to use those on the exam. That is enough of a justification. It's really short, but if you do not put that, you're going to lose a full mark. If you do not say that you're able to do that because of the fundamental theorem of calculus, for me on the exam, I would have a tough time just writing FTC. I'm a very extra elaborator when I would write exams. I would write out, by the fundamental theorem of calculus, I'm allowed to say g prime of x equals f of x.
Do you get the question?
And I would get
Hi, attendance check for Rowan Highland.
Yeah, he showed up late. I just haven't changed it because I was.
Okay, I'll adjust it here. Thank you.
I can do it. That's okay. Perfect. Let me see if I can get in there quicker. Come on, come on. Oh, they're in. This is weird. Come on, come on. I'm excused. Oh, they got in there before I did. Okay. So then f prime of 8 will actually equal f of 8, not the slope, f prime of 8. Okay? And so the answer is just 1.
I knew it.
Part B. We know that g prime of x, by the fundamental theorem calculus, is f of x. That means the double derivative, g double prime of x, is f prime of x. Find all the values of x on the open interval at which the graph of g has a point of inflection. Give a reason for your answer. Points of inflection, g double prime of x, which is equal to f prime of x, has to change sign. Has to go positive, negative, or negative, positive. What do we know? Which is where g prime equals f changes from decreasing to increasing. Okay? So in other words, if we had g double prime and we had some point c and it changed sign from negative to positive, that would tell us on g prime that we're going from decreasing to increasing. Now g double prime is f prime and g prime is f. So do we have any places where f changes from increasing to decreasing or vice versa? Yes. F right here at -3. It's going down, then going up. Then also here at +3, it's going up, then going down. And then at 6, it's going down, then going up. Yes.
Would it matter that it's a cusp at 6?
It won't matter that it's a cusp at 6 for the following reason. So a function can still have, so we always used to say two things for an inflection point, right? Changing sign and then saying that it's equal to 0. And that happens for 99.99%. Technically, g double prime can also be a critical point where it doesn't exist, so g double prime won't exist at 6 because it's a cusp. But because the original function is continuous and exists, it has to be an inflection point for that reason as well. So it's kind of a weird one in that situation. And this is why we do questions like this, because we want to find those. The more questions we do, the more unique situations we run into, solve them, and then like, oh, if this comes up on the exam, I've seen that once already. Doesn't guarantee that you'll remember all of that and be able to do it perfectly on the exam, right? But chances are better than having seen it, right, only for the first time. Our goal is to try to see every kind of unique thing like 7 or 8 times before the exam. Strategic choice of numbers there. Okay. Part C. Find g of 12 and g of 0. Well, g of 12, the definition here says it's from 6 to 12. That is just the area under the curve from 6 to 12, which is a nice little triangle. That's equal to 9. What's g of 0? That's going to go from 6 to 0, which is the negative from 0 to 6. This is half of a circle, and it will be negative. So it'll be negative 9 pi over 2. And finally, part D. Find the value of x which g attains an absolute maximum on the closed interval. Again, it says justify, so we have to have what theorems we're using. Okay. From this, -6 to 12, including -6 to 12, it attains an absolute minimum either when g prime is equal to 0, which means f of x would be 0, right? Or at an endpoint because of the extreme value theorem. So we have to check all of our candidate points to do this. If you wouldn't say extreme value theorem in this question, you would lose a full mark. They're looking for that extreme value theorem. And they're also looking for that you know that something has a maximum when the derivative is 0. The derivative is 0 at 0 and 6. Technically -6 as well, but that is an endpoint. Our endpoints are -6 and 12. We check all of our values, and we want to find the maximum of g. So we figured out this -9π/2 in the last question. We also figured out this 9 in the last question. You would still have to figure out the 6 and the -6. So it has an absolute minimum at x equals 0, an absolute maximum, which we didn't have to find, at 12. Can you see the other two, how you could figure them out quickly in your head? Right? When you do 6, well, that's the integral from 6 to 6. If you're not moving anything, that's going to be 0. And when you go from 6 to -6, half of it's above, half of it's below. It's exactly the same circle. So those areas would cancel out, whether you went from -6 to 6 or backwards from 6 to -6. So there's two ways you can do that a little bit quicker to see that those are both zeros. And then we get our absolute minimum at x equals 0. This is typical on an FRQ to disguise one of your VT theorems in the middle of it. Not disguise it, but it's like have those, they like to ask those, have those ready at mind. Okay, the fact that the endpoints were included and you're asked for a maximum or a minimum, that's always an extreme value theorem question, where you find your critical points in the middle, but also check your endpoints. So lots of students lose marks on this. Why? They get the right answer, but they only check the middle 2 points. They lose a mark because they don't say the extreme value theorem. They lose another mark because they didn't check the candidate points of the endpoints. Here's our new graph from -6 to 7. Has a horizontal tangent at x equals -2. It's a straight line from 0 to 7. Let R be the region in the second quadrant bounded by the graph, the vertical line x equals -6, and the x and y axes. And we're told that this has an area of 12. So we've got a function g defined by g of x from 0 to x, so we see fundamental theorem of calculus part 1 right away. Find these values, g of -6, g of 4, g of 6. Well, plugging each of those in is just an area function. And we know shapes here. We know from 0 to -6 is the same as -6 to 0. We were told that area was 12, so that answer will be -12. From 0 to 4, since that's a straight line, you can do base times height divided by 2, and it will be 4. From 0 to 6, well, we know this area is 4. From 4 to 6, that area is going to be 1, but it's going to be a -1 because it's below the x-axis. So we can't just go 4 plus 1, instead we have to do 4 minus 1 and get 3. Part B, for the function g, find all values of x between 0 and 6 at which the graph of g has a critical point. Okay? What is a critical point? That's where the derivative is equal to 0. Critical point, derivative is equal to 0, or the derivative is undefined. Fundamental theorem of calculus says that g prime of x is equal to f of x. So again, you have to say that justification that allows me to do that. F of x is equal to 0 at 4. I'm going to double look because part of my head, in my head says at the endpoints, because they're included, 0 and 6 are included, no derivative would exist at those. So I'm going to also include the endpoints 0 and 6 as critical points, because technically the derivative doesn't exist at 0. Or does, wait a minute, okay, let me think. My derivative endpoints, but my actual f of x, no, it does exist. Never mind, these get erased. Can get mixed up with the fundamental theorem of calculus part 1 and part 2. F of x actually exists at -6 and 0, and it's not equal to 0. So this is the only critical point. The function h is defined by h of x from -6 to x of f prime of t. Whew. Find the values of h6, h prime of 6, and h double prime of 6. So here we can plug in things. -6 to 6. This is the fundamental theorem of calculus part 2. That if the derivative is in here, then you can do the antiderivative, which is just f of x, and do f of b minus f of a, and you would get -1.5. Our justification by the fundamental theorem of calculus, h prime of x is equal to f prime of x. That's fundamental theorem of calculus part 1. And I'll put up the answers here so that we can see them. H prime of x equals f prime of 6, which is -1/2. That's the slope at x equals 6. H double prime of 6 equals f double prime of 6, which is equal to 0.